And thanks for understanding this unfortunate schedule. I have a meeting tomorrow, so that's why it's just for me. All right, so today Ben is going to talk about his joint work with the Deb.
That's right. So this is joint work with Debsoumya, who most of you probably know. He's now at the University of Warwick. When we did this work, we were both at here. And I'm going to start talking about a slightly simpler problem, which is a Falconer's problem in finite fields. So Falconer's problem is a very famous problem in geometric measure theory, and this is a kind of combinatorial analog. So we take Q to be a power of an odd prime, and we can define the kind of Euclidean norm of a vector to be the sum of the squares of the entries in the vector. And then we define the distance set of any subset of points to be the set of distances determined between pairs of points in that set. And this isn't actually a distance, but it does share many of the same algebraic properties of distances and has some interesting properties. So the main questions that we're concerned about are, suppose that we know that the distance set of a set E is a strict subset of FQ, then how large can E be? Or a second question is, suppose that the distance set has smaller than some fixed positive density, then how large could the set be? And here's some examples to show that you can have sets in finite geometry can determine relatively small sets of distances. If we take Q to be 1 mod 4, then the square root of -1 is an element of the field. And then we can take a line of points of the form, say, I times A. And here the distance between each pair of points is going to be 0. Hence, the distance set is, the entire set of distances is just 0. A second example is if you have a subfield of FQ, and you take the set of points to be a plane over the subfield, then all of the distances defined between pairs of points lie in the subfield, and so the total size of the distance set is the square root of the number of points, but the size of the set is the square root of is also the square root of the number of points. So here you can have reasonably large sets that have very small distance sets. But the kind of first major result in the area was by Iosevich and Rudnev, who showed that if you have a set of points that's larger than 2 times q to the d plus 1 over 2, then the distance set is, in fact, the entire field. And this is tight when the dimension is odd, but when the dimension is even, the conjecture is that we should be able to improve the exponent to d over 2. And here, with the squiggles, I just mean maybe you could hide some log factors or something. That we're still quite far from being able to show anything like that, so it's not too important what the precise conjecture is. The best general bound is still that d plus 1 over 2 that was shown on the previous page. And there are some improvements to the exponent. For example, in the plane, Hart, Iosevich, and Du and Co. showed that if you have a set of points in the plane of size at least q to the 4/3, so the threshold on the previous page would be q to the 3/2, then you determine a positive proportion of all the distances. And the same bound is known if you have a set of q to the 4/3 points, then not only do you have positive proportion of all distances, but there exists a point in the set from which a positive proportion of all distances occur. That was by myself, Brendan Hansen, and Oliver Roche-Newton. And better than that, bounds are known for prime fields. So the first improvement was by myself and Yorgos Petridis, and then later Brendan Murphy, Yorgos Thangpham, Misha Rudnev, and Sophie Stevens improved our result. And I think that the best exponent there for prime fields is 5/4. But this is not really the problem that I'm going to talk about. But actually, let me give a kind of a sort of fictional story about the easier part of the proof of Iosevich and Rudnev. How would they have written down their proof if they were graph theorists? So let me define S sub r to be the sphere of radius r. So it's a set of points whose norm is, as defined previously, is r. And then G sub r is going to be the r distance graph on the d-dimensional vector space over Fq. So the adjacency matrix here is going to have a 1. So the vertices are the points of Fq to the d. And there's an edge if the distance between there's an edge between x and y if the distance between x and y is equal to r. And this is just, I'm using the set and the indicator function for the set is, I'm using the same notation for that. So that's what the notation is. Then we'll let chi be an additive character of Fq to the d. And there's a lot of useful things known about this. For example, if chi is the kind of all ones vector, then it obeys the identity that it's required to obey. And that's the trivial character. And then the remainder of the characters live on the unit circle in the complex plane, and they give a nice basis for the set of functions from Fq to the d to the complex numbers. So, and the Fourier transform, or the Fourier coefficient of the sphere attached to chi is defined to be this. So we take the sum over the points of the sphere of the character evaluated at that point.
Can I ask something? So here we have, I'm a bit confused with the notation. So SR is a set of points, right?
Yeah, so I'm using the same notation for the set and the indicator function for the set. So SR is a function that takes a value 1 if is a function on Fq to the d that takes a value 1 if the given vector has is in the set S sub r.
Oh, so y minus, oh, so this means y minus x is in SR or not?
That's right, yeah. That's it.
I see.
Yeah, yeah. So it's just a little kind of abusive notation there that I write that use the same notation for the set that I use for the indicator function for the set. Okay, so now A is a matrix whose elements are indexed by pairs of points in Fq to the d. Chi is a function from Fq to the d to the complex number, so it's a we can write it as a column vector, and so we can multiply them and say what happens if you take the product of A with chi. So let's see here. This is just writing out matrix multiplication. We can change right, t is going to be the same as y minus x. So we just change the vector. And now since chi is a character, we know that chi of y minus t is equal to chi of y times the complex conjugate of chi of t. So we can pull it out. And what do we find is that A times chi is equal to chi times the Fourier coefficient of x, of s, that's associated to chi. So the Fourier coefficients of the sphere are exactly equal to the eigenvalues of the graph, of the distance graph. So the theorem of the main technical result of Iosevich and Rudnev is that all of the non-trivial characters, or all of the non-trivial, all the Fourier coefficients of the sphere that are associated to the non-trivial characters of Fq to the d have bounded, have this bound of q to the d minus 1 over 2. And consequently, as we showed on the previous page, the eigenvalues, kind of the non-trivial eigenvalues of the distance graph are bounded by q to the d minus 1 over 2. So here, an nd lambda graph is a graph with n vertices, that's d-regular, where all the eigenvalues except for the main eigenvalue are bounded by lambda. And since all of the eigenvalues are exactly the Fourier coefficients of the sphere, and we know that all of so the trivial Fourier coefficient corresponds to exactly to the first eigenvector, and all the remaining eigenvectors have this bound. And so just is kind of a standard, well-known thing that we can bound this size of the largest stable set in the distance graph. So this shows that if you have a stable set in this R distance graph, then the size has to be at most 2 times d plus 1 over 2. And that's equivalent to saying that if you have more than q to the d plus 2 times q to the d plus 1 over 2 points, you have to determine every single distance. So they didn't write everything in terms of spectral graph theory, but this is the way that we kind of relate the Fourier analysis to kind of more graph theoretic arguments. What I'm going to talk about today is a little bit of a different question. We're interested not just in determining whether a set of points determines a specific distance, but does it determine a more complicated graph? So here, a distance graph H is going to be a graph where we label the edges with elements of FQ. And we say that a set of points contains the distance graph if there's an injection from the vertex set of H into the set of points that preserves the distances. So here's a graph H with 3 vertices where we've labeled the edges of H with 1, 2, and square root of 5. And the question is, well, does this set E of points here contain that distance graph? And the answer is yes. Here's a map that so that the distance between phi of y is the same, and phi of x is the same as the distance between y and x over there. The distance between phi of y and phi of z is the same as the distance between y and z over there, and similarly for x and z. So this is an embedding of the graph of this particular triangle with those specific labels into this particular set of points. So to give a kind of example of the sort of results that we're interested in, if we have a sequence of distances, then we can give a path with those that has those distances, labeling the edges. And so in 2014, this group of authors, Bennett, Chapman, Covert, Hart, Iosevich, and Pakianathan, showed that if k is not too large, meaning k is going to be little o of q to the d plus 1 over 2, and E is a subset of points of the d-dimensional vector space over fq, and the size of E is bigger than some constant times k times q to the d plus 1 over 2. So q to the d plus 1 over 2 is the threshold that we had for finding any single distance. Then, for any sequence of k elements, non-zero elements of fq, there is a path with that sequence of distances in E. So if we take k is equal to 1, this is basically the result of Iosevich and Rudnev, and it's more general. And so my result with Debsoumya is for distance trees. So here, if we have a subset of FQ, I'm going to say that an R distance tree is a tree with where all of the distances only come from that set R. So it's a little bit more restrictive than what I talked about before. But our theorem is this. So suppose that you have a subset of the non-zero elements of FQ, and delta is an integer. Then every set of points contains every R distance tree with at most cardinality of E minus, well, this thing here. You've got, so this says nothing, there is a, it's not written down explicitly, but obviously this says nothing if the size of E is smaller than 30 times delta, T times delta to the 1/2 times Q to the D plus 1 over 2. So that's, this number here is the kind of, I can't use the dot, I'm sorry. This number is the threshold. And once we're past the threshold, the size of the tree that we find is everything that's left over. And so the maximum R degree, basically we have a tree where every edge is labeled by some distance. And if you look at a vertex, I'm going to call the R degree of a vertex the number of edges incident to that vertex that have the label R. So in particular, if you take a very chaotic coloring where every vertex only has one, you know, if every edge, every vertex could have a different distance for every edge connected to it, then we could take delta as, well, it has to be at least 2, I guess, in the statement. But that's what I mean by R degree. So for example, if we take R to be the set of all of the distances, then what the result shows is that we can take the threshold Q to the D plus 2 over 2. So we're losing a square root of D factor in the threshold. And we get every distance tree with maximum degree 4 and at most half of the vertices. So this is what we mean by almost spanning. So the size of the tree is comparable to the set of points that we find. We can find every tree that's of size comparable to the set of points. But we have some bound on the degree. And I wrote every distance tree with maximum degree 4, but this should be maximum degree 4 in each distance. So the degree of the underlying tree could be extremely high, but it's required that each distance is only duplicated 4 times at each vertex.
Also, maximum R degree, is it the number of edges with distance
Same distance, yeah.
Same distance.
Yeah.
Uh-huh.
Right. So we can compare our theorem to the one that I showed earlier for paths. It's a little bit, I mean, the main difference between our theorem and the one before is that we're looking for trees that cover almost the entire vertex set, or the almost entire set of points that were given. Whereas the previous one was looking for paths of size k. But we can consider paths with size k. So here's a corollary to the theorem. If E is a set of points and the size is at least square root k times q to the d plus 1 over 2, then we contain every k distance path. And this follows by taking delta equal to 2 and assuming, and then weakening the conclusion of our theorem by quite a bit. So what would happen if we said delta equal to 2 in our theorem? Well, we get something for trees, in fact, but what we could, one easy corollary is that we would contain every tree on at most half of the vertices that used at most k different colors. But we would contain every path that's on at most half of the vertices that uses k different distances. But every path that's of length k only uses k different distances. So if we throw away all of the extra information coming from the theorem, this is what we get. Does that make sense?
Wait, in your theorem there's no k, right?
That's right. There's no k. So our theorem is we're replacing t. T is the number of different distances that are used.
Okay.
And we're replacing that with the length of the path. So if you have a path of length k, then you use at most k different distances. So that's where the K came from. This corollary is much weaker than the theorem that it comes from. We've thrown away a lot of information. But
because in your results, the length of the tree can be very large.
Exactly, because in our result, the size of the path would be very large. It would be almost everything. Whereas here, it's some fixed K, which is smaller. So they are only finding things that are of size q to the little o of d to d plus 1 over 2, and the size of the point set is k times q to the d plus 1 over 2. Whereas we find things of size, the paths that we find naturally in our theorem have size comparable to the set of points that we start with.
But the path in the corollary, the path you find is like T1, T2. You have to have
That's
this
right.
thing.
That's right. That's right.
But how do you get it from the theorem? Your theorem doesn't have
Doesn't have any k.
any. Oh, is T this?
So we just say t. Well, we have a path of length k. It uses at most k different distances.
Okay.
So then we just say, well, what we'll do is we'll find every path without worrying about the length. Just find every path that uses only k different distances. And in particular, that covers the paths of length k.
Oh, I see.
Yeah.
So when you say the distance tree, you already have labeling there. So all possible
That's right.
distances you have it.
That's right. But even with this restricted corollary, we still get a quantitative improvement to the previous result. Because what we have is if the size of our point set is larger than square root of k times q to the d plus 1 over 2, then we can find every k distance path. Whereas Bennett, Chapman, Covert, Hart, Iosevich, and Pakianathan, they showed that if the size of E is at least k times q to the d plus 1 over 2. So what happened is we improved the k to square root of k.
Mm-hmm.
Yeah. So even, I mean, the main interest is a kind of qualitative improvement that we actually get an almost spanning tree. But even if we only are thinking about very small paths, we still get a quantitative improvement over the earlier results. And there's a very similar kind of, there was work done on trees before. So here's result by Thang Pham, Stephen Singer, Michael Tate, and Du. And they show that if you have a tree on k vertices, and the size of E is at least k squared times q to the d plus 1 over 2, then we contain almost the expected number of disjoint copies of T. This was their theorem. So E divided by k is the maximum possible. If you're if somehow you manage to cover your entire point set with trees, you would get E divided by k. So we're missing q to the d plus 1 over 2 copies of the tree, and the tree has k vertices in it. So we're missing the size of the point set we start with is q squared times q to the d plus 1 over 2. And then we can remove there's some set of k times q to the d plus 1 over 2 vertices that we can remove. And then what's left over we can cover with copies of the tree. So what we can do is, again, kind of improve things by a square root factor. So if the size of the set is at least k times q to the d plus 1 over 2, then we cover all but the expected number minus q to the d plus 1 over 2 points. And there are various different ways. I mean, here there's a lot more parameters to play with. I'm just choosing some particular setting of parameters to make a comparable theorem. But the main difference here is that we improve, let's see, their k square we improve to a k. And there's we can improve it over other ranges of parameters by taking different corollaries to our theorem. But the idea here is we want to find a bunch of disjoint copies of the same tree. So what we can do is use one of the distances that's already represented in, we can use one of the distances that's already represented in the tree and then link things together on the leaves. And I mean, there's many, many different ways to do that. So we could find, but that's how we make how we can make our theorem comparable to previous work.
Here, the tree T means it's distance tree, right? You have a hidden distances you have to satisfy, right?
That's right. That's right. Every tree has a labeling of the distances, and so the idea is that we're given an arbitrary labeling, an arbitrary tree with an arbitrary labeling, and we have to find that specific tree. And if that's true for an arbitrary tree, then it's true for every tree. If it's true for an arbitrary tree in some class, then it's true for every tree in that class. So next thing I want to talk about is the how close to being tight is our result. So there's a lot of different parameters floating around here. First of all, we have Q and we have the dimension. And even in the case that we're looking for if we're looking for exactly one edge, we know that our theorem is tight. The theorem of Iosevich and Rudnev is tight in the case that D is odd. In the case that D is even then it's still an open problem. So I'll just leave those parameters and not worry about them. So if D is odd, then the dependence on E and Q is tight. If it's even, then we don't really know the situation. The remaining parameters that I'm interested in are delta, which is the maximum R degree, T, which is the number of distances used, and something that doesn't show up in the error term is the size of the set E. But, and I'll explain a little bit more why I'm interested in talking about that. So let's talk about the delta first, which is the degree. So if you have a if you take a fixed point x and you take a random set E, then we would expect to have roughly the size of the set divided by q different points at distance r from our point E. So if the size of the set is small over, q to the d is the total number of points in the space. So if the size of the set E is small o of q to the d points, then the kind of typical R degree of a point is going to be small o of q to the d minus 1. And we can arrange it so that that's not just true of a typical point, but it's true for every point up to some constant factors. So for this extreme range, for this extreme point, the dependence on delta is possible because if we plug q to the d minus 1 in as for delta, then the claim is that we could find every spanning single distance tree. The conclusion of our theorem would be that we can find every single distance spanning tree of size q to the d. And we certainly cannot find, and we can't replace q to the d with anything smaller than q to the d and still have a true statement. So for single distance trees, when the degree is as large as possible, our theorem is the dependence of our expression on delta is tight. So if you replace this dependence on delta by anything smaller without changing any of the other parameters, you would end up with a false statement. There may be certain ranges of parameters where the dependence on delta could be improved, but in the sense you can't just replace delta with delta to the 1/2 with any smaller dependence on delta. Now we conjecture that the error term should depend inversely on E. So if you take a larger set of points, it's not that you can just remove a constant number of. What our theorem shows is that if you have a sufficiently large number of points and you fix the other parameters, then there's some constant number of points that we can remove, and we can cover everything that's left over by some tree. But when you're attempting to embed the tree, you actually get a lot of flexibility from the size of the set. So we kind of conjecture that if you get a larger and larger set of points, you can cover all but an absolutely smaller number of points. And we have some evidence for this. For single distance trees, we can prove a stronger result. Or I say we can prove a stronger result, but actually it's an easy corollary of some other difficult result, which I'll mention in a second. So the theorem is as follows. For any delta, there's a constant such that for every set of points that's bigger than some function depending on that constant times q to the d plus 1 over 2, every single distance tree. So here we're taking r to be 1, the size of the distance set to be 1s. With at most e minus q to the d plus 1 divided by e. So we know that the size of e is going to be at least q to the d plus 1 over 2. So if e is roughly q to the d plus 1 over 2, this is comparable to the previous result. But as e gets larger, we're covering all but a smaller fraction of the remaining points, if that makes sense. So we have an inverse dependence on e here, and it's the same at the at the starting point, at the threshold of q to the d plus 1 over 2. And this is a corollary of a recent theorem, or a theorem from last year of Han and Yang on embedding spanning trees into expander graphs. But it's limited in that they're only working on a single expander graph, whereas we have lots of different distances, so it's not clear. We don't know how to use their results to address the. But I mean, for sure, there's a conjecture here, which is that their term should be depending on e. And there are methods that can achieve that in some special case. So I don't think that this is I think this is possibly something that could be solved. I'm not sure. So we also have a dependence on the number of different distances. And we conjecture that at least with the right statement, maybe you couldn't get the R degree here. But at least with the right statement, we could remove the dependence on the number of distances entirely. So kind of our strongest conjecture is that for any degree delta, there's a constant so that if the size of this given set of points is bigger than that constant to the little over d, to some little over d function times q to the d plus 1 over 2, then you contain every distance tree with all but, this is basically the same function that we had on the previous page for the single distance trees. So our conjecture is that you can just improve this corollary of Han and Yang's work to find not just single distance trees, but every distance tree, even with different number of distances. So that's our. Now, let me say a few words about our proof and how it differs. The previous work in the area is basically using kind of direct arguments using Fourier analysis. So our result is dependent on the result of Iosevich and Rudnev, who used Fourier analysis to calculate the eigenvalues of the distance graph. At least that's the way that I say their result. They wouldn't say it that way. That's the way that I talk about the result. And so what we do is say, okay, Fourier analysis is done, now we can do combinatorics. And just work using combinatorial methods on ND lambda graphs. And kind of the technical background is that there's a famous result by Friedman and Pippinger from 1986, who showed that expander graphs contain small trees. And this has been improved many, many times. And so kind of the key technical graph theory part of our paper, what we do is we prove a colorful generalization of a theorem of Haxell from 2002. And what Haxell did is she basically improved the 1986 proof of Friedman and Pippinger so that she can find almost spanning trees instead of just small trees. So here's the the actual statement of Haxell's result. So delta is the degree of the graph that we're trying to find. What we're going to do is we're going to try to find the tree T inside some given graph G. And G is a good expander. In order to apply the theorem, G needs to be a good expander in that small sets have to expand by factor delta, and large sets have to expand by factor delta plus the size of the tree that we're looking for. So if there exists some m, and we'll say all the sets that are smaller than m expand by factor delta, all the sets that are between m and 2m expand by delta plus a factor of k, then we can find all the trees that have at most k vertices and maximum degree at most delta. Gamma x is the, I think the external the open neighborhood of x. I actually can't remember if it's open or closed neighborhood. But I think you can write it either way, but it may affect exactly the, yeah. Okay, so here's our generalization. And so now instead of giving a single family, instead of being given a single graph that has to have a certain expander property, we're given a family of graphs, and they have to have some joint, they have to be good expanders in the following sense. So if we're given any set of vertices, and now the vertices, X now is not a set of vertices. It's a set of vertices, each vertex being labeled by some distance. So we're thinking about X is our graph G, our family of graphs G shares the same vertex set. But we're actually looking at a set of vertices, and at each vertex we're going to give it a label. And then when we say what is the neighborhood of this set of vertices with the labels, is you actually have to follow. If you look at the vertex, you're only allowed to use edges with the color that you've got the label. And so
is it the same thing as you just consider disjoint union of the graphs, but then the set X is like you always collect copies of the same vertex, consider at the same time?
So X is a subset.
Oh, it's a subset.
Subset of the Cartesian product. So it's not, X itself is not a product.
Uh-huh.
It's not the product, yeah.
But if I say I take the universal graph G as a disjoint union of G1 to GT, and then do I have the same property as the first one of the previous theorem, or?
It's a little, I think it's a little different. I mean, well, yeah, maybe that is the same thing. Yeah. I mean, there's not really a lot of interaction between the different graphs going on. Yeah, I think that is.
You could take G1 and you could take them all to be the same.
Can take them all to be the same.
Then it reduces to the.
Then it reduces to the previous statement. Yeah. If you take them all to be the same graph, then it does reduce to the previous statement. If they're different graphs, it's a little bit of a different statement. So the proof is not that different than the proof of Haxell's theorem. I think it's mostly about finding the right statement to say. And making it, yeah. And so the conclusion is that we find every tree with maximum degree of R in each color. And yeah. So this is So once we have this, it's not immediate that, I mean, we have some family of ND lambda graphs, which are the distance graphs for each distance in our set. And then we have some hypothesis here, and we have our set E. So what we're looking at is the induced subgraph and induced so these families here are induced subgraphs of some set G, but actually these properties aren't satisfied initially, so we have to do some manipulation in order to apply. It's not immediately clear that we can actually apply this theorem, but with a little bit of work, it's not too hard. It's not too hard. So let me, I have about 15 minutes left. Let me take the next 10 minutes or so to give a proof of a special case of our theorem. I assume probably most people here are familiar with ND lambda graphs and the expander mixing lemma. It just says if you have ND lambda graphs are very good expanders. If lambda is small, they're very good expanders in the sense that if you have any pair of set of edges, then the number of edges between them is roughly the expected number if the sets are large. So, I mean, the previous statement that I just wrote down about the size of the largest stable set of an ND lambda graph is just a special case of the expander mixing lemma where you take x and y to be the same set of vertices. So here's the special case that I want to prove. Let's suppose that we're given a family of ND lambda graphs, G1 to GT. So these are going to be the t different distance graphs. And suppose that we have a subset of the vertices. All these graphs are on the same vertex set, and we're given some fixed subset S. This is the same as E in the previous setting of the vertices. Then the induced subgraph on S contains every t colored path with at most S minus 2 times n lambda over d times t to the 1/2 vertices. And n lambda over d is q to the d plus 1 over 2 in our setting. Or 2 times q to the d plus 1 over 2. So this is if you look at the constant, this constant is a bit better than what we're claiming, but the theorem is only for paths instead of for arbitrary trees. So if you plug in the bound on lambda that was proved by Iosevich and Rudnev, then this is the threshold that we get. It's 4 times square root of t times q to the d plus 1 over 2. And so this proof is completely independent of the more general proof for graphs, but it gives basically the same result. I mean, it's actually quite a lot simpler than the general proof. So what we do is I'm going to describe an algorithm. The input to the algorithm are the t different graphs, each one being an ND lambda graph, and a set S and a path P. And what we'll do is we'll find the path P, the given path P with the specified edge labels we're going to find in the different graphs. So the idea is that each edge in P has a label of either something between 1 and t, and when we find it, we have to use the edge from that particular graph. Okay. And we got a picture. So here's the input is P, and notice that there's different colors on the edges. These colors I didn't specify, but they correspond to some integer between 1 and t. And initially we put all the vertices of S over in the set L. And then we have a set U which starts out empty, but at the at some point during the execution of the algorithm, it will contain a copy of P. That's the claim. That's what I'm going to prove. And then we have T different sets, R1 to RT on the right. And initially they're empty. So the first step of the algorithm is U is empty. So what we do is we remove a vertex from L to U. We don't care which one. So now we have a vertex in U. Now the next case is suppose that we have at least one vertex in U, and there's an edge from the last, so U is a stack here. There's an edge from the last vertex of U going into the unused vertices L, and the color of this edge is the correct color. So what we have is a partial copy of P, and we're trying to find the next edge of P. And there's an edge into L that has the right color. So what do? We just move that vertex over into U, like that. Case 3 is, well, there's no guarantee. Maybe at some point we're looking for a light green edge. None of the light green edges from this vertex are going over into L. So we can't move anything over. So what we do is we move this vertex into the set Ri, where I is this light green color. So the colors are corresponding to the integers 1 to t, and so are these sets on the right. So this is the light green colored set. And so now we have a vertex in R sub I. And that's the whole algorithm. So some easy observations is that in every step of the algorithm, either a vertex is moving from L to U, or a vertex is moving from U to one of the sets on the right. They never move to the left, and they always move to the right, so eventually everything's going to be over on the right. And whatever vertices are in U, it's always going to be a copy of the first few vertices of the P. I mean, in theory, maybe you always get stuck on the first vertex and there's never any edges, but whatever vertices are in U, it's always going to be a copy of the first vertices of P. And the kind of key observation is that so the light green, remember R sub I is the set that corresponds to this light green color. And the reason that we moved the vertex from U over into R is because there was no edge from that vertex going into L. So at every stage of the algorithm, there's no edge from R sub I in G sub I and the vertices of L.
So I was small.
Yeah, so I mean, and now we know that we know that each of these graphs is an ND lambda graph, so we can just apply the expander mixing lemma to find a bound on the size of the product of R sub I and L. So we'll just now the plan is to use this observation together with the expander mixing lemma to bound the size of the product of R sub I and L for each I. So we know that there are no edges between R sub I and L. That means that the d divided by n times L times R sub I is less than lambda times the square root of L and R sub I. This is just the expander mixing lemma because this is 0. And so in particular, if you solve this for the product of L and R sub I is less than n times lambda divided by d squared for each I. So if we take so what we'll do is let's just run the algorithm until the size of L is square root of t times n lambda over d. So every round, either L decreases, every round, either we're moving a vertex from L into U or vertex from U into one of the R. And we can always do that, so the vertices are always moving to the right. So at some point in the execution of the algorithm, the size of L is going to be root t times n lambda over d. And at that time, we know that each Ri has size at most 1 over root t times n lambda over d. And there's t different elements of R, so in total we have 2 times root t times n lambda over d vertices between L and all of the r's combined. And that means that any vertices that are left over have to be in U. And so if the size of P is less than S minus this particular 2 times root t times n lambda over d, then we had to find it at some point. Yeah. And so just this, just this simple proof already gives a big improvement over the previous work of Bennett. The proof for the graph theory proof is more complicated, but it's still using, yeah, that's it.
Thank you. Any questions?
Could you find some cycle in that your graph with the designated distance?
It's a little complicated. I think that finding, like just knowing, if all you know is that a graph is a good expander, I don't think you can find arbitrary cycles. You can find many different lengths of cycles, but you can't just specify the length of the cycle and then find exactly that one. It might be possible in specifically the distance graphs for long lengths because you don't have it's a little, yeah, the answer is it's not, the cycles are a bit harder and it's not clear. Like I don't know exactly what I would conjecture as far as cycles, but I would say that just because something is impossible for general expanders doesn't mean it would be impossible in the setting. That our proofs only use the fact that it's expanders, but I mean these are not arbitrary expanders, these are specific graphs. And in fact, we know that we want to go for the Falconer distance problem, the eigenvalues are correct. What we want to show is that there's no, the size of the maximum stable set is smaller than what you'd get from just the spectral arguments. And so similar, I think that there could be similar, I think it would be interesting to use some more geometry than just because at the beginning of the proof we just said, okay, here are the Fourier coefficients in the sphere. Now let's forget that we're even in FQD and talk about expander graphs. So I think that that's not really the right thing to do. But that there is more. We can continue to work in that direction. We haven't exhausted everything that can be done in that direction, but that ultimately something like finding every cycle of a certain length or greater might, especially like large cycles. Yeah, it might be I think it might be quite interesting. Yeah.
If you change the distance function to maybe some quadratic form, then do you expect to have a similar theorem, or is it like complete nonsense?
No, everything makes sense. You just have to, you have to redo the Fourier analysis. Sometimes it's harder.
Like, is it known to be like expander graph?
Yeah. So, for example, let's see. I mean, you have. So there's 2 different questions. One question is, well, let's replace just the norm, the sum of the squares, with some quadratic form. Yes. And that doesn't change the problem at all. This is there's only 2 different quadratic forms over FQD, and basically what we get is we get one of them when Q is 1 mod 4, and we get the other one when Q is 3 mod 4. And so switching to the other quadratic form, nothing changes in the problem actually. Another question would be, well, let's take instead of looking at the quadratic form that's evaluated on the difference, we could take, for example, the dot product between the 2 vectors, or some other polynomial function of these 2 vectors. And so the dot product has been extensively studied, and these results, I mean, you know, if you calculated the proper, if somebody calculated the appropriate Fourier coefficients associated with some function, then we could just plug it into our framework and everything goes through and falls out. But some of the, depending on the function that you're working with, the problem may be harder or easier. Like one of the things that Duan Ko worked on, he came in here and talked about it, is that he had thought of a function where he could prove get the right exponent for even dimensional. So it's just something that looks kind of like a distance, except that he designed it in such a way that he was able to prove the improved bound for the even dimensional Falconer distance problem. So if you take, for example, take his special function, then we could get even better. We could also get better results in the even dimensional case using that. But yeah, you can take a lot of what we're doing is quite abstract and not really depending on the specific function in this.
Other questions? If not, let's then